All right, good afternoon, everybody. Today we're going through two notebooks. So I'm going to talk about floating point types, but there's not much to say about the floating point types that you don't already know. And then we're going to look at arrays in more detail. So the floating point types, most of the time you're using float or double as your types to represent real numbers. There is a long double, but a lot of computers don't actually support it. So they're not. So it's a lot of computers don't have 128-bit floating point support. So you often, if you use long double, you just end up with a double anyway in many cases. If you want to know about the about the limits related to float, they are found in float.h, that header file there. If you click on that link, it takes you to this section of the CPP reference for the limits. You'll see that because there's these three types, there's going to be a corresponding constant for most of the types. Right? So for example, float min, so that's your, what is that? That's the minimum, that's the smallest positive float number that you can have. Double min is the smallest positive double value that you can have, and L double min is the smallest positive double, long double value that you can have. Sorry. So normally for any constant here, you'll normally find a different one for float, double, and long double. One that's somewhat interesting is this one that's right here. So float decimal digit, and double decimal digit, and L double decimal digit. So those are the constants that are defined. If you type in a floating point literal, so using base 10, then those values are the minimum number of digits that you need to, minimum number of digits, right? Yeah, minimum number of precision, so digits after the decimal point, so that you can convert your base 10 number to a double, to a floating point type, and then convert the floating point back to the same literal. Right. So for doubles, you need at least 17 digits of precision in order to guarantee that going from your literal to a double back to your literal always works. That's really, so I did mention in a lecture a few lectures ago that it's actually quite hard to convert from is to get the string representation of a double. And this constant is related to that. All right, if you want to do any math, then you're probably looking at math.h as for your functions. For example, if you want the value of infinity, that's in math.h. Oddly enough, it's not in limits.h. It's in math.h. Sorry, it's not in float.h. It's in limits. It's in math, sorry. So if you include that header file there, you get access to the constant infinity. Right, that's just the most positive value that you can have. The most positive non-finite value that you can have. There's a function isInf that returns true if the value is infinite, and it returns false if it's not. The constant nan is short for not a number. That's the value that you get when you do floating point division by 0. When you do 0.0 divided by 0.0, you get not a number. If you do any operation with a value that's not a number, you also get a value that's not a number. Not a number is very weird. So the way it behaves according to the floating point standard is unusual. So the standard says that not a number is equal to nothing, not even itself. So if you have a value that's not a number, you can't use equals equals to determine whether or not it's not a number. That doesn't work. Instead, you have to use the standard library function is not a number. Right? So this is going to print 1. D is infinite. It'll print 2. D is infinite. It will not print 3, and it will print 4 is not a number. Whoops, sorry. Control Z, Control Enter. There we go. Right. So notice that number 3 doesn't work because no value is equal to nan, not even itself. Right. Nan is strange. All right, if you want to compile a program that uses math.h, most of the time, but not always, strangely enough, you have to link to the math library. Right? So if I wanted to compile that program right there, you would type in that. Right? So compile the program, specify the name of its output, and then you have to tell the linker you need to link to the math library. So you need the -lm. So m is short for math in this case. The L is an L, not a 1. So -L for GCC tells it to link to that library. Right? If you're using third-party libraries, you'll have to use -L to link to those libraries. Inside math.h, there's also a whole bunch of mathematical functions that are similar to the ones you would see in Java. The big difference is, because you can't have a function with the same name in C, there's a different function for each type. So sine f is sine of an angle for float. Sine is sine of an angle for double. And sine L is sine of an angle for a long double. Right, so you'll see 3 corresponding functions for every one of these functions inside the standard library. Right, so there'll be a cos f, a cos, and a cos L, for example. Right, square root is just square root. Right, most of the function names are the same in C and Java. Pow, so that's x to the power 2. Pow will compute. You can use, I think you can use I think you can use a floating point value there. Just a second while I look it up. C, headers, and then math, and then pow. Yeah, so your exponent can also be a floating point exponent. Right? So you can compute 2.5 raised to the power 3.1, for example. Oh, actually, and then a max is a floating point. So f max is floating point max. And so if you run that, whoa, what happened here? Oh, yeah, you can't, this doesn't link, yes, this is the problem. So if you try to run this in Jupyter, well, if you try to run it in Jupyter on my computer, it doesn't work because Jupyter doesn't link to the math library. So there's a symbol lookup error here. Printf we looked at briefly when we talked about types. Right? So if you want to print a floating point number, the conversion is %f. Right? Remember, if you print using %f, you end up with 6 digits of precision after the decimal place. You can change that by by specifying dot precision in front of the f. So for example here, I'm going to print the square root of 2 using 12 digits after the decimal point. Here I'm going to compute x raised to the power 2 and use 2 digits of precision after the decimal. Here I'm going to compute the max of 2 values, and I'm going to print the result using 1 decimal point of precision. If there are fewer digits of precision than the value that you're printing, it rounds. Oh, again, I think we're getting yes, we're getting, let me run this in my console, sorry. So this is math demo 2. So GCC -o math demo 2. Let's see, and I have to link. Okay, so that's not right. Something's going on. Hang on, sorry. Boom, boom. I probably did not put in the conversion. Yeah, I didn't put them in. Oh wait, they are here. What's going on? Printf %. This is not behaving the way it should. Sorry. Did I compile the right program? Oh, I compiled the wrong program. Sorry. That's what's happening. Math demo 2. There's a math demo. There's also a math demo. Sorry. There you go. Right. So there's 12, 2, and 1 digit of precision. There's something else that you can specify. This is also on the assignment. So you're allowed to specify a number in front of the decimal point as well. So if you specify a number in front of the decimal point, that tells printf how many digits or how many spaces, the minimum number of spaces it should use to print the result. Right? So if I put in something like 20 here, And this is 2, so I'm going to use 4 here. Wait, 5. And 1 digit of precision, so I'll use 6 here. And recompile the program. And then rerun it. So the 20 here says use at least 20 spaces to print the result, at least. So that's the minimum number. So if you actually count the number of spaces there, that'll be 20. Right. The 5 here says use at least 5 spaces to print the result. So if you count here, 1, 2, 3, 4, and 5. Right. So in other words, it inserts a leading space in the result if the output is shorter than that number. Right? And so here, if you say 6.1, that's use at least 6 spaces, one digit after the decimal point. Right? So 1, 2, 3, 4, 5, and 6. Right? So that's what those two numbers mean. Right? And don't forget, if you use G instead of F, then the precision is the total number of digits in the number, not the number of digits after the decimal point. Okay, that's basically all there is to say about float, because there really isn't much to say about it. It behaves the same as, float and double behave the same as they do in pretty much any modern programming language on a modern computer. All right, so back to arrays. So we've talked briefly about arrays already. Here we're going to go look at them in more depth. So in particular, we're going to look at how to use an array in a function, or how to return an array, or what happens when you try to return an array from a function. Okay, so let's just skip through. So I guess to remind you, one of the big differences between C and Python or Java, right? You get no array bounds checking, right? So the language doesn't check your indexes for you to make sure they're valid. So if you try to index into an array with an invalid index, the result is undefined, right? So in other words, you don't know what's going to happen. If you're trying to read a value from the array, you'll read some random value if the index is invalid, right? Or you'll end up with the program crashing, because when you try to read into that memory is not accessible at that point in time for whatever reason, right? If you try to write into that value and the index is not valid, you'll either write over something else if you're unlucky. You'll write into memory that's not being used if you're luckier, or you'll try to write into memory that's not accessible and your program will crash. Right? But either way, no matter what happens, the result is undefined, right? So you can't tell what's going to happen. Okay, so to declare an array, so when you declare an array in C, you get the array object, right? So int x3 gives you an array of 3 ints, right? So in other words, you have access to those. You can use x0, x1, x2 already. That's one of the differences compared to Java. In Java, you would have to make a new array object. Right? Again, square brackets to access the array, so it's exactly the same as in Java. When you do this, though, the values are not initialized. So that's the other difference in Java. In Java, if you make a new array, the values get initialized to 0 if the type of the array is primitive. Right? That's not true in C. So that array x is completely uninitialized at this point in time. Right? If you try to use x0, x1, or x2, whatever value is there is completely random. If you want to initialize the elements of the array and the size of the array at the same time, you can use an initialization list, right? So x square bracket, 1, 2, 3, inside of braces, makes an array of size 3, right? And its values are 1, 2, and 3. Right? If you run it, you're going to get 1, 2, and 3, right? No big surprise there. If you specify the size, and you also specify an initialization list, then the size of the number of elements in the initialization list must be less than or equal to the size of the array. Right? So here I have an initialization list of length 5, but the array has size 3, so the compiler is going to complain. The compiler complains, and does it compile? It does not compile. Right? So it tells you you have too many elements in the array initializer. The 4 and the 26, that tells you what line and what column the error is happening on. Right, so that says on line 4, I think that's column 26. Right here is 26. That's where the error has occurred. If you use fewer initializers than the size of the array, this is a, sorry, there's a 3 missing here, like that. So if you use fewer initializers than there are elements in the array, all of the remaining elements in the array get initialized to 0. I forget what that's called in C. It actually has a name. So there you see 300. Right? So the language guarantees that you will get zeros in the rest of the array if you use an initialization list. You can also specify the indexes if you want to. So for example, I can write, sorry, not 0. I want to write 2 equals 3, like that. Right? And so that says initialize the array x, set element 2 so that its value is 3. All the other values in the array will be set to 0, like that. Right? So you can, if you want to, specify the indexes. It's uncommon when you're working with arrays, but I'm sure you can cook up with a problem. You can find a problem where you'd want to do this sort of thing. Okay, so in C, don't forget that strings are just arrays of car, right? So for example here, my string str is just an array that contains CISC220, right? Don't forget that strings in C though, a string literal in C always has a null terminator on it, right? So at the end of that string is the numeric value 0, right? Even though you don't write it yourself when you write the literal. Right? So the length of this string is 7, but the size of the array is actually 8 in this case, right? Because you have the null terminator on the end of that string. You have to be a little bit careful when you're working with arrays, arrays and strings. Right? So for example, if you don't use a string literal to initialize the array, so instead if you make the array and then you populate the array yourself, like that, right? You have to remember to include the null terminator yourself as well, right? So this one works just fine. If you printed out the string, you'll get CISC220, right? If you comment out this line, I suspect it still works, but it's not guaranteed to. So it still works, but it's not guaranteed to work. And if you try to do this in a larger program, it almost certainly won't work, right? So that string is not correctly terminated, and you won't. You'll get a different output. Right. I don't want to, well, we can try to, give me 1 second here to see if I can break this. No. And one more. No, still not working. So even though it prints out the correct string in this case, that's not guaranteed to work. Okay, you can have a const array, right? So a const qualified array is an array whose elements are read-only, right? So if you qualify an array with the modifier const, then all the elements of the array are also themselves const, right? So if we make an array x of length 3, right, and put const in front of the array, in front of the type, initialize the array to 1, 2, 3. This works just fine. So if you run this, you get x1 equals 2. Right? If you try to write into x1 or x0 or x2, the compiler will complain. Right? So it'll tell you that you're trying to assign a read-only location x1 in this case. Right? So const qualified array, all the elements of the array are also const. The only way you can set the elements of the array are with an initialization list like this. Right? So there's no other way to, well, sorry. I suppose you could call the function, which would also work, I suppose. But once the values are set, you're stuck with those values. You cannot assign to an array variable. So here I've got two arrays x and y. They're both of length 3. Right? If you try to assign to either variable, you will get an error. Right? So as soon as you make a variable whose type is an array, so in other words, as soon as you say square bracket after the name, right, or square bracket number, you can't assign to that variable. Right? You can initialize it. Right? You can initialize it where you create it, but as soon as you try to assign, you'll end up with an error. Right? So here it says error assignment to an expression with array type. Right? It won't let you do it. You can work around this problem though, and we'll see how to do that in a later lecture. So strings are arrays, right? So it's a very common error that you will make two string variables and make them as arrays, and then you want to reassign a string so that it refers to a different string. That doesn't work in C. Right? So if you make an array str1 and you make an array str2 and you try to assign to str1 after you've initialized it, again it complains. Right? Assignment to an expression with array type. Right? So that doesn't work either. So this looks like, this appears to be that you would think that, or this makes you think that working with strings in C is very awkward, right? I can't reassign to a string, but there is a way to work around it. Okay, so one way to work around it is to, instead of doing assignment, is to copy the elements of the string, of the first string into the second string. Right? And so one way to do that would be to write your own loop, right? Because it's just an array after all. Right? So if x is the array 1, 2, 3, and y is the array 10, 11, 12, right? Then if you want to write x equals y, instead of writing x equals y, copy the elements of y into x using a loop, like that. Right? So if you run that and then print out with the elements of x, you'll get 10, 11, 12. So not surprising. Right. Okay, if you want to copy an array though, it's typically easier, well, is it really easier? Once you get used to it, it's easier to use a standard library function to do the copying instead. Right. So there's a function called memcopy that copies chunks of memory from one location to another. Right? So it copies a chunk of memory pointed at by source into a chunk of memory pointed at by dest, right? So source and destination. The third value there, count, is the number of bytes to copy, right? So what does all that mean? Right. All right, so the amount of memory that you're copying is specified, whoa, sorry, I forget, I can't do that, by the number of characters count, right? Now count is measured in terms of bytes. So if you want to copy something that's not a car array, right, or not a car, then you have to figure out what the size of the thing is you want to copy. Right? So in other words, if you're going to copy an array of, say, n ints, right, you're going to do n times size of int to get the number of bytes to copy. Right? So remember in C, for most of the standard library functions that take in some amount of memory as a parameter, it's always measured in bytes. So for example, if I want to copy the elements from y into x using memcopy, right, then what you need is a pointer to the source memory, right? So I want to copy the elements of y, so I need a pointer to the first element of y. Right, so my source is the address of the first element of y. Right? The destination is the location in which you want to copy the memory into. Right? So I want to copy into x starting at the first element of x. So my destination pointer is the address of the first element of x. Right? Now, if you remember from either the last class or the class before, you can just write this as y, and you can just write this as x. But if you want to be explicit about it, the address of x0 and the address of y0 are fine. Right? So there's your source pointer. There's your destination pointer. Right? How much memory do you want to copy? Well, I want to copy 3 ints. Right? So you need to do 3 times size of int here. Right? And now this also works. Oh, or not. Implicit conversion of function memcopy. Oh, where? Oh, sorry. It's in string. Hello? There we go. There, that's better. Right, and so now that also works. Right. So this looks awkward the first time, well, the first several times you use it. But eventually, when you get used to working with pointers, this becomes natural. Right? So in other words, if you write a lot of C, using memcopy is a lot easier than writing a loop yourself. It's almost certainly faster, too, because memcopy is going to use an operating system call to do the copy, whereas the loop, C has to do all the work itself. Okay, so memcopy, though, so you can copy an array into another array, but the way that memcopy is specified, right? So it takes in a pointer to some memory that you want to copy, right? And it takes in a pointer to some memory where you want to copy into, right? You don't have to use the start of the array as those pointers, right? So in other words, you can say, I want to copy from the middle of the first array into the start of a second array. Or I can copy from the start of the first array into the middle of a second array, right? You just need to get a pointer into the middle of one of those two arrays, but that's easy to do, right? So here I've got an array of size 6, and I've got an array of size 10, right? And I want to copy 4 elements from the middle of y into, where am I doing it? Somewhere into the middle of x, right? So I want to copy, so the source is going to be the address of y4, right? So that's y0, that's y1, 2, 3, 4. So I'm going to copy, starting from the 14, I want to copy that into the address of x2. So x2 is, there's x0, there's x1, there's x2. So starting at the 14, I'm going to copy these values into here, starting into the third element of x. Right? And I'm going to copy 4 values. So we're going to copy the 14, the 15, the 16, and the 17 into index 2, 3, 4, and 5 of x. Right? And all we're doing is you just adjust the source pointer and the destination pointer. Right? So they point at the appropriate elements. Right? So if we run this now, oh, sorry, I forgot string again. There you go, right? So you get 0, 0, 14, 15, 16, 17, right? So you can copy a subarray into another subarray, for example, right? You also don't have to copy just arrays. So you can copy a single int into a single int if you wanted to, right? Or you could copy a single double into an array of double. It's even worse than that. You can take a double, you can copy a single double and copy it into an array of int, and that will do strange things. But the function will let you do it. Okay, so you can use memcopy to copy strings too, but normally you don't use memcopy to copy strings because there's a special function for strings called strcopy, right? And we'll take a look at that probably in the next class or two, right, when we talk about strings. All right, so arrays and pointers are, arrays are not pointers, but the language lets you treat them almost as though they were. Right? So the name of an array is synonymous with a pointer to the first element of the array. Right? So what does that mean? It means if you have an array, ARR, then the name ARR is synonymous with a pointer that points at the first element of ARR. Right? So in other words, it's synonymous to the pointer that points at ARR0, right? Or it's also equal to the address of ARR0. Right? So for example, here's my array, right, containing the elements 1, 2, and 3. So it's an array of double values. So I can make a pointer to a double, right? And I can say that it's equal to the address of the first element of the array. Right? So here I'm not using the fact that the name of the array is the same as the pointer to its first element. Right? I'm actually taking a pointer to the first element, right? The address of the first element. Now, that line right there, so that condition right there, is that pointer equal to ARR? Right? So remember, two pointers are equal if they point at the same element of an array. Right? So P is a pointer to the first element. ARR by itself is also a pointer to the first element of ARR. Right? So that's going to print, yes, they are in fact equal. Right? Okay, so this lets you get around the problem of you can't assign to an array variable. Right? So you can do something that looks like, so instead of assigning to an array variable, what you do is you take the array and assign it to a pointer. Right? So here's my string, right? It's an array of car. Right? Here's a pointer to car called P. Right? Now I can't write string equals something, but I can write P equals str. Right? So I can make a pointer that points at the first element of the array, and then say that the pointer P now points at that string str. Right? If you want to, you can dereference the pointer. Right? So if I dereference P, right, that gives me the first character of the string, right, which in this case is going to be the capital C. Right? Notice that I can print the pointer, right, and treat it as though it were a string. Right? So in other words, I can print the contents of that string using the pointer instead of using str, right? And it works just fine. You can also do the following. Right? So I can make a new array or a new string. So string 2 equals, I don't know, CISC235. Right? And now I can do P equals str2. Right? And the compiler is perfectly happy with that. Right? So whereas you cannot assign to two arrays, right? You can't assign to an array variable. The way to work around it is just to make a pointer that points at the array, the first element of the array, and then assign to the pointer, because you can always assign to a pointer. Right? If you want to swap two strings, though, you have to literally swap the contents of the two arrays. Right? So in other words, you have to copy the contents from one into the other. Oh, so you still can't take an array variable and assign a pointer to that array variable. Right? So here is our string. That's a character array. Right? I'm going to try to make a copy of that string. So copy 8 is a string that is an array that's big enough to hold the contents of str. Right? This works fine. Right? So taking a pointer, making a pointer that points at the first element of str works fine. Right? I can't say copy equals P, though, right? Because you can't assign to an array variable whatsoever. So here the compiler complains. Right? Assignment to an array type again. Right? So no matter what you do, you can't assign to an array. Right? You can assign to a pointer that points at the array, but you can't assign to the array itself. If you need to swap the contents of the array, the only way to do it is with a loop or a function. Okay, so in the memcopy example, I showed you how you can get the address of an element in the middle of the array. Right? It's just address of, ARR, and then an index. Right? But that's not the only way to do it. Right? So here, if I want the address of the second element of the array, right, I can ask for the address of the second element of the array. Right? But there's another way to do it. So in C, pointers have what are, you can perform arithmetic with pointers. Right? Now, arithmetic with pointers has a very special meaning. Right? So if P is a pointer to an element of the array, then P plus 1 is a pointer to the next element of the array. P minus 1 is a pointer to the previous element of the array, assuming those elements exist. Right? So more generally, if P is a pointer to the element at index j, right, then P plus I is a pointer to the element at j plus I. Right? P minus I is a pointer to the element at j minus I, assuming they exist. Right? So in other words, instead of writing, hang on. let's just keep on going here. I'll do that in a second. If you want to dereference them, right? So if I take that pointer, p plus I, and dereference that pointer, right, then that gives me the element at index j plus I. Right? Similarly, if I take the pointer p minus I and dereference it, that gives me the element at array at ARR j minus I. Right? So let's look at an example. There is an array of length 7. Right? P is a pointer to the fourth element of the array, so that value right there. Right? So P is a pointer to the 3. P plus 2 is a pointer to the element that's 1, 2 elements down the array from the pointer. Right? So P plus 2 is the element, is pointing at the element whose value is 5. Right? So P plus 2 is the same as if you had written array 3 plus 2. Right? P minus 3, right? So remember P is a pointer, is that pointer right there. It points to that element there. So P minus 3 points to the element that's 3 in front of it. So that one, that one, that one. So it's, in other words, it's the same thing as pointing at the array element at the front. If you dereference the pointer, you get the element itself. Right? So dereferencing that pointer actually gives you the element 5. Dereferencing this pointer actually gives you the element 0. Right? Using dereferencing, you can actually change the element. Right? So here I'm going to change P6. P6, ARR6. Right? So if I want to change the last element of the array, right, I can use the name of the array. Remember, the name of the array is just the pointer to the first element of the array. Right? So ARR plus 6, oh, sorry, Control Z. ARR plus 6 is just the element at index 6 of the array. If I dereference it, I can assign it a value. So I can change the last element of the array to minus 100 in this case. Right. Okay, so P points at the 3. P plus 2 points at the 5. So if I print that value out, I should get 5. Right. P points at the 3. P minus 3 points at the 0. So if I print that element out, I should get 0. ARR plus 6, that's just the element at index 6 of the array, right? If I dereference it. So that's the last value there, right? So if I set that to minus 100 and then print out ARR6, I should get minus 100. Right? So you can use pointer arithmetic to move pointers around in an array. Right? And it turns out that a lot of C code will in fact do that. So instead of using indexing, a lot of C functions will simply take a pointer into an array somewhere, possibly the first element, possibly somewhere in the middle, and then it'll use pointer arithmetic to move through the array. There's a special pointer for arrays. Right? So if you have an array, then the language guarantees that there is a pointer called the too far pointer for that array. Right? So if you have an array of length n, then the language standard guarantees, right? So you have an array length n, right? So I have int ARR length n, right? Where n is bigger than 0, right? You know that the largest possible index for this is ARR n minus 1. So int last. Right? So the last element of the array is at index n minus 1. Right? If you try to use ARRN here, right, the language says that's undefined behavior. Right? You'll end up with you might end up with some value that's incorrect. Well, you definitely will. You'll end up with a value that's not in the array. Right? You might crash your program. The language actually guarantees, though, that the pointer to the element that's 1 past the end of the array is guaranteed to exist. Right? So in other words, if you have my array here, ARR has length 4, 5, 5. 0, 1, 2, 3, 4. Right? So if this is ARR, right, then the language says that the pointer to here, so that's ARR plus n, right? It says that that pointer exists, right? And it's called the too far pointer. Right? So the pointer exists, but you can't use it. You're not allowed to dereference it. Right? If you try to dereference it, anything can happen. However, it does exist. Right? So in other words, it's the pointer that's one past the end of the array. Right? The reason why that pointer exists is because a lot of old C code will use that pointer to indicate the end of the array. Right? So in other words, they'll write a loop that uses a pointer, and the loop will run as long as the pointer is not equal to ARR plus n. Right? So we're going to look at that in just a second when we iterate over, over an array using some pointer. OK, pointer comparisons. So if you have a pointer into an array, then less than, greater than, less than or equal to, greater than or equal to are all defined. Right? So if P and Q points to elements of the same array. So they have to be pointers of the same array. If they point into different arrays, then I believe you get an error when you try to compile your program. Right? So if you have two pointers that point, I'm not sure what happens if you try to do that. If you have two pointers into the same array, though, then you can then you are allowed to use less than or greater than, less than equal to, greater than or equal to. Right? So if P points at the element ARRI, and Q points at the element ARRJ, right? Then P is less than Q if I is less than J. Right? So in other words, if P points at an element that's in front of J, then P is less than Q. Right? If they point at the same element, then P less than or equal to Q is also true. Right? If P points at an element that comes after ARRJ, right, then P is greater than Q. Right? So in other words, you can compare two pointers for their relative location in the array. Right? A pointer comes before another pointer or is less than another pointer if it comes before one. Right? So in other words, the comparison operators can be used to compare the locations of two pointers. All right, now before we can iterate over an array, we also need the assignment operators. Right. So plus plus, minus minus, plus equals, and minus equals, they're all defined for pointers. So if P is a pointer, then P plus equals n assigns the value of P plus n to P. Right? So in other words, it moves P n positions to the right, assuming n is positive. Right? P minus equals n, again, assuming n is positive, right, moves P n positions to the left. Right? P plus plus moves P one position to the right. Right? P minus minus also moves P one position to the left. Right? Plus plus P and minus minus P. If you think about what they do to the pointer, then they also move the pointer one position to the right and one position to the left. Right? Now these operators are a bit odd in that those expressions there, they all produce a value. Right? So if you write P plus equals n, you can actually take that value and assign it to another variable, which is strange, but that's the way it works. Right? So the value of P plus equals n is actually P plus n. Right? So in other words, if I make a pointer Q and write Q equals plus P plus equals n, then that makes Q equal to the pointer P plus n. Right? P plus plus and P plus plus P, a lot of new programmers think they mean the exact same thing. They don't. And that's true in most languages where plus plus is defined. Right? So p plus plus, its value is just p. Right? So the value, if you use p plus plus as a value, then it's just p. Right? So it's just the pointer p. The operator has the side effect of then moving p one position to the right. Right? So p plus plus is called the post increment operator. Right? Gives you the value of p, and then it moves p one position to the right. Plus plus p is different. So plus plus p adds 1 to p, so moves p one position to the right, and then gives you the resulting value. Right? So it's called the pre-increment operator. Right? P minus minus and minus minus p do the same thing. Usually it doesn't matter which one you use, but occasionally you'll run into somebody who's tried to be clever, and then it matters. So you have to be a little bit careful about which operator you pick. So, so without being clever, let's just use p plus plus and p minus minus. So here's my array of 7 values. Right? I'm going to move forwards using pointer arithmetic instead of using an index. Right? So I'm going to move forward through the array starting at the front. Right? So the front of the array, a pointer to the first element of the array is just ARR. Right? I can move forward in the array by writing p plus plus. Right? Here plus plus p works and p plus equals 1 works. They all do the same thing in this case. Right? How far do I want to go? Well, I want to go until I reach the too far pointer. Right? So the too far pointer is just the array plus the size of the array. Right? So there's 7 elements in the array, so the too far pointer is just ARR plus 7. So as long as my pointer p is less than the too far pointer, right, we can do something with p. Right? And here I'm just going to print out the value of p. Right? So I'm just going to dereference p and print out its value. Right? Similarly, you can go backwards. Right? So if I want a pointer to the last element of the array, right, that's just ARR plus the size of the array, so 7 minus 1. Right? So it's ARR plus 6. So that's a pointer to the last element of the array. I want to move forward in the array each time, so p minus minus. Right? Minus minus p also works here. P minus equals 1 also works here. Right? When do I want to stop? Well, I want to stop when I finish processing the first element of the array. Right? So as long as my pointer is greater than or equal to the first element of the array, right, I'll do something with p. Right? And so here I'm just going to dereference p again. Right? So this program is just going to print 0, 1, 2, 3, 4, 5, 6, and then 6, 5, 4, 3, 2, 1, 0. Right? So forwards, 0, 1, 2, 3, 4, 5, 6, and then backwards, 6 through 0. Right? All using pointer arithmetic. Right? All right, so that's probably a good place to stop. In the next class, we'll finish off this notebook. So we'll see what happens when you have an array and you want to use it as a parameter to a function, or if you want to return an array from a function. Right? We still won't be able to do those after the next lecture. We need another lecture after that before we can actually do those. But we'll see what happens when you try to do that.